So we're looking at the test results. I have included a marking scheme so you can see where I was attributing marks. The red arrows are each worth 1 point. The first question says, a substance found in rotting meat contains 58% carbon, 13% hydrogen, and 27% nitrogen. It has a molecular mass of 102. Determine the empirical and molecular formula. The first thing we do is to assume a 100-gram sample, which allows us to turn the percentages into gram amounts, which we did here. We then divide it by each one of the molecular masses to get how many moles of each one of the substances, each one of the atoms will be present in a 100-gram sample. We then divide by the lowest number of moles, which is the moles of nitrogen. In the hopes of getting integer amounts, we find it gives us 2.5, 7, and 1. So we can't have 2.5 atoms within a molecule, so what we're led to do is to multiply by 2, which we did here, and that's the lowest number that's going to give us a set of whole number values for the number of atoms within a molecule. So we get an empirical formula of C5H14N2. When we find the empirical formula weight by multiplying by the molecular masses of each one of the atoms involved, we come up with 102. And we're told in the question that the molecular mass of the actual compound is 102. So what that tells us is that the empirical formula is the same as the molecular formula. And I would have expected you to write both of those things within in the answer. Some of you wrote it only once, but you should specify exactly that the empirical formula is this, and that the molecular formula is that, and provide proof of it. The next one, aniline consists of carbon, hydrogen, and nitrogen. Combustion of 9.7 milligrams yields 6.6 milligrams of water, and 1.46 milligrams of nitrogen. Its molecular weight is 93. What is its empirical and molecular formula? The first thing I did is I scaled the experiment up 1,000-fold. It doesn't change any of the proportions, and it allows you to work with grams instead of milligrams, so you don't have to work with exponents all the time, or there's fewer of them. So it wasn't necessary to do any calculation for the nitrogen except to find out what percent of it constitutes of the mass of the original compound. We show a typical combustion equation where you have complete combustion, all of the carbon content of the molecule turns into CO2, all of the water is coming from the hydrogen in the molecule, and all the nitrogen just comes out as nitrogen. So we had 6.63 grams of water being formed. We divide by the molar mass of water to find how many moles of water, and then we multiply by 2 to find out the moles of hydrogen. Then we switch back by multiplying by the molar mass of gram. We multiply by the molar mass of hydrogen to find out the grams of hydrogen, and then we find the percent of hydrogen in the sample, it's 7.64. We already know the mass of nitrogen, so if we these two quantities, we can find the percentage of the nitrogen, the percentage of the hydrogen, and then by subtraction we can find the percentage of carbon. What I did is to subtract the mass of hydrogen, which I found here, having added it to the mass of nitrogen to find in the original sample how many grams of carbon were left, and then from the grams of carbon I found the percent percent composition of carbon in the molecule. So we had now all three percentages, the percent carbon, the percent hydrogen, percent nitrogen, which allows us to continue to the second phase of the question, which is to assume 100 grams, which allows us to, again, turn all the percentages into gram values, divide by the molar masses to get the proportions of moles in a 100-gram sample, divide by the smallest number of moles to get, hopefully, integer values. We get very close to that, 5.99, 1, and 7.06. That's very close to 6. That's very close to 7. So we say that the empirical formula is C6H7N. We then calculate the empirical formula weight based on this formula, and we get 93.1. We were told that the actual formula is 93, so that again tells us that the empirical formula is the same as the molecular formula, and therefore the molecular formula is also C6H7N. Third question. We have a limiting reagent question. Chromium reacting with chlorine gas to form chromium chloride. So the first step was to determine which one of the substances is going to run out first. So I discovered how many moles of chromium, how many moles of chlorine, and then I used the stoichiometry, beginning with one of them. I picked one. I picked this one. I started from the chromium amount, multiplied by the stoichiometry of chlorine versus chromium, and found that I needed 0.236 moles of chlorine. Well, we had more than we needed. We had 0.262, So that means that the chromium is the limiting reagent. Chromium is going to run out before the chlorine. So we're going to start our calculation from chromium. And we did that. We started with that number, which we obtained here. We multiplied by the stoichiometry of chromium to chromium chloride, which is 2 to 2, as you can see here in the balanced equation. You always have to balance the equation. If you don't balance the equation, you're going to get the wrong answer when you do your stoichiometry calculation. So it's 2 to 2. We get the same number of moles of chromium chloride. We multiply by the molar mass of chromium chloride, which is 158. And when we multiply those two numbers, we get 24.973. We're only allowed 3 significant figures. And so you get 25 grams of chromium chloride according to our calculations. The last question was the bonus question, in which I asked, if a cube of gold weighs 50 pounds, how many atoms could you count along one edge of the cube? How tall is the cube? And I gave you 2 pieces of information. Actually, you need a third one, the density of gold as well. I forgot to give it at the beginning, but I did give it later. So 1 kilogram is 2.2 pounds. The molar mass of gold is 196 grams per mole. So we start out with 50 pounds. We convert it to pounds using this conversion factor, putting pounds on the bottom because we want to eliminate pounds. We want to cancel that out. I'll show you how that works. Pounds cancel. And then we want to cancel kilograms. So I put kilograms on the bottom, multiplied by 1,000 because there's 1,000 grams in a kilogram. So we have 22,000 grams of gold. We then divide by the molar mass of gold, which allows us to multiply cancel grams. So we get moles of gold, 150 moles of gold. We multiply by Avogadro's number, 6.02 times 10 to the 23, which gives us 6.9 times 10 to the 25 atoms of gold. Now those 6.9 times 10 to the 25 atoms are in the form of a cube. And we know that in a cube, length times width times height gives you the volume. So whatever those atoms measure, we know that any number of atoms times in length times any number of atoms in width times any number of atoms in height, or length, width, height, as it were, would give you 10 to the 25. So if we take the cube root of this number, we'll know how many atoms are lined up along one edge. Turns out it's 410,832,492.7. We're only allowed to report to 4 significant figures, so we're going to say 411.8 million atoms are along one edge of the cube. Then using the density formula, density equals mass over volume. We transpose volume and we transpose density, so we get volume is equal to mass over density. 22,000 grams divided 19.3 grams per centimeter cubed, that's the density of gold. Grams cancel, we get a volume in centimeters cubed, 1,175 centimeters cubed, and we do the same thing here. We take the cube root of this number to get 10.55, and we round it to 3 significant figures in this case because the density is only reported to 3 significant figures. So the height of the cube is 10.6 centimeters. So final answer, the cube is 10.6 centimeters high, and one edge has 411.8 million atoms. Any questions?